Hello everybody. Today we're going to finish up our entire chapter on circuits and current, and what this is going to do, this should get us through everything that is expected to be on the AP exam. The end of this PDF file that you have has a bunch of sample questions. Some of the math involves some multiple steps, some calculus, etc. I'm not going to go through that all that in depth. You can ask individual questions on that and kind of pour over everything. But that's going to be the plan. So after this particular lesson, you should have everything you need regarding the AP exam. So starting off here, we're on slide number 16 is where we left off. And what this is looking at a concept, a device known as a galvanometer. A galvanometer involves some magnetism type qualities behind it, which really are irrelevant for what we're talking about. Basically, what you have is a coil of wire. As the current goes through, it causes this blue needle to be deflected, and all you have to do is put some markings in the background, and now you have an analog device that can tell you what the value is. We can use this to measure resistance, current, or voltage. We call this a multimeter. I'm going to jump ahead 2 slides. We've used these in class before, and so if we scroll down just a smidge, what you'll notice is you can measure DC voltage. You can measure AC voltage, which is what you get out of the holes in the wall. You can measure down here DC amperage right here, or current. And then down here you have ohms, so you can measure resistance. So just turn the dial in terms of whatever it is you want to measure. There are a few holes at the bottom into which you would plug in. You've got the common black wire for your ground, and then you would plug in the red wire depending on what it is you wanted to measure, whether it was your current up here, your voltage down here, whatever happens to be. So that is commonly referred to as a multimeter. In our class, we've really only used it as a voltmeter, which is why I always call it a voltmeter. But if we were to use this, the current goes through, causes the needle to deflect. What happens if you send too much current through? Eventually, this blue wire is going to reach a maximum amount of deflection, and any extra current is not going to cause any change in your blue wire. We would call this burying the needle or maxing out the needle. And so what we talked about last time is that your ammeter, your current meter, should be connected in series with whatever it is you want to measure, whatever device you want to measure. You want the ammeter to be in series with that. That way, whatever is going through the ammeter, went through your resistor. We've got a real crude drawing right here. If I know the current through that resistor, connect an ammeter in series. Same current has to go through each one of our rules. Now, what happens if I have too much current going through, but I still want to get an accurate measurement? Simple. I just have to divert some of that current away from the needle. And as long as I can divert a known amount of current away, I can very accurately measure the remaining amount of current. So if I have a needle that can measure accurately up to 1 amp, and I've got 10 point something amps coming through, if I can divert 10 amps away, I can measure the remaining fraction and get a very accurate value of 10 point whatever that answer may be. And so if we think about how is it that you would divert current away from your actual coil, away from your device, you would need a second branch. You would need another branch of your river, so to speak, to pull some of the water, some of the charge away, so that we have something measurable. And what that is referred to as, what that's known as, is a shunt. And so what you're going to see here is IFS. That's going to be the current when we are at full scale. So right here, if your current is too large, a shunt is needed to remove some of the current to keep the coil readable. So looking at our picture here, if I've got too much current coming through A for the coil to read, I open up right here, R shunt. Now some of my current's going to go through, and it's going to allow this to get an accurate reading again. And I can change what the resistance is. You saw that picture of the multimeter. There was multiple locations for the dial. Click, click, click. I can choose whichever range I wanted to measure. And what you're doing is you are actually changing the resistance of your shunt. Now I'll ask you a question. I'll give you 2 seconds to answer. You can always hit pause if you want to think about it. But what kind of resistance would you want your shunt to have if I wanted to pull away more and more and more current from my coil? What kind of resistance would I want my shunt to have? 2-second pause for you to pause it if you want. And what we would need is a lower and lower and lower amount of resistance. The lower the resistance, the more current is going to go pouring through that resistor. So that dial, 2 slides ahead, that dial, as I am going through and measuring the different types of current, I can measure 2,000 microamps, 20 milliamps, 200 milliamps, 10 amps. All those, you're clicking to a lower and lower and lower resistance for your shunt. That way you can pull away more and more and more current. So if we continue moving downward, we have AB, so that is going to be the voltage between the voltage that's going that's dropping across our resistor. Our ammeter. We said in a previous presentation we want the overall resistance to be we want it to be pretty small. That way it's not requiring much voltage to be used. Otherwise, using an ammeter affects the current of your device, and what's the point in measuring with an ammeter that ruins your answers? It'd be like using a meter stick, and every time you use a meter stick you change the length of the thing you're measuring. That doesn't make any sense. So I come down here, I've got my junction rule here, the current going through the coil, the current going through the shunt. I know that the voltage from A to B has to be the same regardless of the route I take. So the voltage going through the coil and the voltage dropping through the shunt, have to be the same. So we have that. And so when I come down here, our ammeter, it's connected in series, but the shunt inside is going to be through parallel. And so quite literally, if you had like a mechanical device, the actual device here, every time you click that dial, you are making a connection to this one or this one or this one, and every single resistor has a particular value, which means we know exactly how much current is going to go through it, which leaves us with the remaining amount of current to be measured by our coil. That's how we use a galvanometer for an ammeter. We can use the same device. This is slide 17 for a voltmeter. It still involves current going through a coil and things like that. So that first portion here, nothing has changed. If I slide on down, now we're connected in a voltmeter. So as a voltmeter, right here, we want our voltmeter to be connected in parallel. That way the drop from here to here through my resistor is the same as the drop here to here through my voltmeter. I don't want a lot of current going through here, so what we're going to do is make sure that our our resistance for the voltmeter is really, really, really high. If it's really high, hardly any charge is going to trickle through here, and all the charge continues going through the device, leaving it effectively unchanged. Now, what happens if I have my coil and I've got a value from my coil? What happens if we bury the needle? Well, I've got too much voltage to measure. I need to use up some of that voltage somewhere else. And we know that when things are connected in a series, they share the voltage. So if I have too much voltage here, I throw in a shunt. This is going to require the use of some voltage, leaving a measurable amount for our coil. If the voltage is too high, remove some voltage with your shunt. And again, question, 2-second answer time, hit pause if you have to. If I want to pull away more and more and more voltage, what's going to have to happen to the resistance of my shunt if I want to pull away more and more voltage as I measure higher voltages? 2-second pause. I'm going to need a really, really high resistance to keep the current consistent through this whole thing, because it's a series, same current throughout the entire branch here. To keep the current the same, the higher the resistance, the harder I have to push, which means more voltage is required to move charge through my shunt. So as I click through, one slide up, as I click through my different voltages, 200 millivolts, 2000 millivolts, 20 volts, 200 volts, 1000 volts, as I go through, I'm clicking through and I'm going to a higher and higher and higher resistance. That's the opposite of the effect we saw for our ammeter. Every resistor that was lower was pulling away more Here, every resistor that's higher is pulling away more because I'm comparing voltage versus our current. So back to that original slide. So sliding on down here, and so going from A to B, we have a series. So that means that I have the whole voltage from A to B is going to be the voltage drop here and the voltage drop here. And so if I use some distributive property type ideas, I get the same current through every single device, and they add up. REQ is just the sum total, and I can distribute that through, and I end up with the voltage drop through the coil and the voltage drop through the shunt. They have the same current because it is a series. So we connect the voltmeter in parallel, but the shunt inside has to be in series. And again, if I draw kind of a crude schematic kind of picture here, as you click through the dials of a real-life device, you're going to be clicking from one branch to the next, to the next, to the next, adding in a new shunt each time. The more resistance the shunt has, the higher voltage I am able to accurately measure. Remember, the whole point of a shunt, pull away a known amount of voltage, and you can measure accurately whatever little bit is left. And so again, there was our picture. And so depending on how you're going to connect it, that's why you have different locations for different things. So if I'm measuring my current right here, I have to use this one. If I'm measuring something else down here, so that's why we have our different holes there. You can go to the hardware store and buy just a voltmeter or just an ammeter, but it's pretty common to find a pretty inexpensive, I mean, you can probably get these for under 20 bucks, a nice cheapy one. Getting yourself a multimeter, and you can use it for whatever you need. And so the last concept that we have to talk about for this chapter are RC circuits. R stands for resistor, C stands for capacitor. So an RC circuit, not an RC radio-controlled car. RC stands for the resistor and the capacitor. So what we know is that when we connect to a capacitor that is uncharged, we connect it to a battery, what's going to happen is the charge is going to build up and build up and build up, and as it builds up, the current slows down and slows down. We saw a light bulb start bright and get dim, and then when we discharge it, it starts bright and gets dim as the charges pour off of that capacitor. And we know that all of our wires have some kind of resistance in them. What we're going to do is take all that resistance and put it into a single resistor here. Either that's all the combined resistance of the wires put together there, or maybe we actually have a real-life resistor, a light bulb or something that is in there, which makes the resistance of the rest of the wires pretty insignificant because I got a big resistor right here. So we've got lowercase letters A, B, and C, so we can look at the voltage from A to B, from B to C as we go through. S1 is going to be a switch, which is just a convenient breakpoint in our system. We've got resistor R, we've got capacitance C, and then we have our EMF up here. And so what we're going to do is we're going to see that the charge built up on the plate will vary with time, and we're going to see, or we have seen, that the current also varies with time. And so what we're going to do is we're going to use lowercase letters for time-dependent currents and time-dependent charges. That's the common way to do it, is use lowercase letters. And then looking over here in red, the loop rule is always going to be true, even if things are in a constant state of change. The loop rule is still always going to be true. So what we're going to do is we are going to scroll on down here. We are going to start by closing the switch. So at time 0, we close the switch, and right when we close that switch, nothing has been built up on the plates yet. 0 charge. Which means that I have a lot of charge that's going to flow because we've completed the circuit. Charge is going to flow in the form of current. Remember, as our, well, we'll get to that in a second. The voltage across BC, that was our capacitor. You can look at that PDF file as I kind of show here, because I can't really, zooming out kind of shrinks everything too much, so you can kind of look at it separately. But BC was our capacitor. We have no charge built up on the capacitor, so there's no voltage from B to C, which means all of our voltage is from A to B. So if our battery gives us an EMF, our resistor is currently using it up. Sometime later, charge is increased, and remember what that means. When the charge increases, our battery, our EMF, is now encountering some, I don't want to use the word resistance because resistance has a special physics meaning, but it is encountering pushback from the capacitor itself. If I scroll up for just a second, we remember that if this is the positive side, positives have been pushed onto this plate, and these positives push back, repel the new positives, or the next positive that comes through, and the next, and the next, and the next. And as more positive builds up here, the flow is slower and slower until the charge built up here gives us a strong enough push to negate the push from the battery. So a little review there on how our capacitors work. So what's happening as time goes on? Charge is getting bigger, current is getting smaller. And I have my V equals IR for my resistor, and I have QVC for my capacitor. Why is there a negative sign? Because if I go from B to C, let's scroll up again, B is the positive side, C is the negative side. Going from the positive to the negative, that's going to be a drop in potential. So in traveling from left to right, I go with the current, lose some potential. I go from the high side to the low side, lose some potential. So that's why we have a negative Q over C. And then much later, air quotes, much later. So an infinite amount of time goes by. We have maxed out our capacitor, QVC. Obviously, that right there is our voltage. So I get QVC from a max. I have no more current flowing, which means my resistor has no voltage drop because nothing is flowing through it. If you dry up the river, there's nothing to flow. And then here we have all of our voltage is QVC right here for the voltage of our capacitor. So when it comes time to do the loop rule, what we have is voltage from the battery minus the voltage used up by my resistor minus the voltage we have stored up in our capacitor, and that has to all equal 0. At time 0, this term is 0. At time infinity, this term is 0, which is where we get these two terms over here. And if we wanted to do a graph, we can look at this. So if we took our black lead of the voltmeter, that's our ground, that's our 0, and we check it with the red. So basically whatever our red probe from the voltmeter touches, that's the change going from black to red is what we're going to get on our reading. So if we go from A to B, there's going to be a drop, so we get a negative voltage down here. We get negative voltage on our capacitor as well, and you can see these two graphs are a mirror image of each other. What's the total voltage of the battery going to be? Our EMF right here, and that's going to be the sum total of the red and the blue graph. So everywhere along here, you add up red and blue, red and blue, red and blue everywhere, and you're going to get this line nonstop. And this is actually just the loop rule. So that's the beginning of our conversation about RC circuits. So if we, what just happened here? Let's skip forward too many times. So here we go. So charging an RC circuit, this is going to be slide number 20. This is going to have some heavy math in it, so I'll go through the math quickly, and you can go over it again and again and again as much as you need to, or you can send me a message and ask a question. So what I have here is my battery, my EMF. I've got a resistor and a capacitor and a branch together. Can't use one without the other based on the way we set this up. I've got a dual throw switch. I can throw the switch down to S1 and complete the bottom, leaving the top untouched. I can throw the switch up to S2, completing the top, leaving the battery cut out. And so what we're going to do is we are going to figure out how to determine charges, voltages, and currents related to time, actual values of time. After 3 seconds, how much current do we have, things like that. And so it's going to depend on how much resistance I have. It's going to depend on how big my capacitor is. Right from the start, I can look at this and you know what? The bigger the capacitor, the longer everything's going to take to charge up. The bigger the resistor, the longer it's going to take, because this is going to slow down the process if it's big. This, if it's big, simply needs more charges to fill it up. It's just going to take longer. I got to fill up a bigger tank. So I can see that the time is going to be dependent on R and C, it appears. But anyways, we'll see how that works out. So what I have here is the loop rule. And our goal is, what is the charge? Depending on time, we want a function for charge. So what we have here is our loop rule. And I know that I is the rate of charge flow. So I can replace I with dq over dt. We did that at the beginning of this this whole chapter, the previous lesson. So what we're going to do is we're going to combine R and C. What we need to do is we need to get Q, where we can do an integration with Q. I have Q, dQ, and dt, so I need to get the Q's together, and I got to get the T's together. Combining RC is going to be a smart decision. So as we scroll down, we end up with, if we go through it, we multiply C through the entire thing to get rid of C here, we get our RC. But I got to do it over here too. C times E, that is my total amount of voltage, that is the capacitance. When we do this, that actually represents the total amount of charge we're going to be able to store. So we can kind of keep that in mind. We can use that as an abbreviation to kind of clean things up a little bit. So if we continue to scroll down here, I'll scroll down so we can see a whole bunch of stuff all at once. We'll start right there. So what I'm going to do is I'm going to, again, I want to get Q isolated. So what you're looking here is just algebraic steps to get Q isolated, and it comes up to be, it turns out to be dQ over Q minus Q final, which is going to be our total amount of charge. On the other side, we get dt, and we get this negative 1 over RC constant. So we bring that out, and what do? We integrate. Add up all the little bits of time, and you get time. We're going to go from 0 to time t. We start off with charge 0, and we're going to end up with some charge Q. So we're going to integrate with these limits. So integrating this side, easy. This side, I have to do a U substitution. If I let U represent Q minus QF, du and is equivalent to dq, and I end up with du over u, and hopefully we recognize that as the natural log. So you know, learning about how and why this works out is some pretty complex math, but once we have it, it's a real simple, easy, just follow the rules kind of integration. So we end up with putting our substitution for u, putting it back in here for our natural log. We have q and we have 0. So again, I'm just kind of progressing through with the math. And once I do that, I put in a q and I put in a 0, I do my subtraction, I end up with this right here. And we want to solve for q. Q equals is what we're looking for. So I got to get rid of natural log. So I'm going to use e to the, so we're using our mathematical, our concept of e and natural log. So if I take this right here and make that the exponent of e, I get e to the natural log of, and that just cancels out, and I end up with this here. So now I have a way to start solving for q. And again, I'm just going to go through algebra, and here it is. The amount of charge that we are going to have is going to be equal to the total charge we're going to get at the end multiplied by this. This is going to be some kind of a decimal. What percentage of the total do we have at 1 second, 2 seconds, 3 seconds, and so on? If I come over here, we can look at our total charge as C times our EMF. If I divide C over here, Q over C, that's going to be the voltage that my capacitor has at some moment in time. So I have an equation to figure out the voltage or the charge stored up based on time. And it's got the same term. This term is simply a percentage. At time equals 0, e to the 0 power is 1. 1 minus 1 is 0. At time 0, no charge. At time 0, no voltage. Well, that seems to make sense. If we send t to infinity, e to the negative infinity power is going to be 0. So I get charge times 1, I get EMF times 1, and Q equals QF. V equals our EMF. So that's our charging method. And what this means, this gives us a new term. Skipping forward one slide, RC, R times C is this term, going back, R times C is this term that we have right in the exponent. I've got negative t divided by RC. Well, think about this from a mathematical standpoint. I'm doing e to some exponent. Our exponents have to be unitless, which means that in order for this to work, t divided by RC, RC must be a time. Say resistance, ohms, capacitor and farads, or capacitance and farads, that somehow gives me time. Well, we double check. An ohm is a volt per amp. A farad is a coulomb per volt. I get a coulomb per amp. An amp is a coulomb per second, blah, blah, blah. And just like that, you get, surprisingly probably, seconds. So our exponent is going to be unitless. And so when you take R times C and multiply it together, you get this little Greek letter here. Looks kind of like torque, right? So this tau letter. This is our time constant. And the time constant is an actual amount of time, an actual amount of seconds. And we know that when we plug in one time constant for lowercase t or two time constants for lowercase t, whatever it is, we know what the outcome is going to be. We know how much charge and voltage we are going to have. The time constant will vary with the resistor and the capacitor. We do a really nice lab if we had the opportunity, obviously. We do a really nice lab where we get a real nice graph, and the graphs are just some of the most satisfying graphs you've ever seen as you see this graph being slowly made, this beautiful curve, but another time, I suppose. But looking at this, what this shows us is, and you can take your calculator out right now, and you can do this. You can put in if t is, if your time, the actual amount of time, is equal to one of these time constants, so whatever r times c is, if time is the same value as that, you have e to the negative first power. All right? And so you plug in e to the negative first power, so I plug in e to the negative 1 power, and I end up with 0.367. But what I have to do is do 1 minus that, and so what I end up with is that whole percentage, the 1 minus, I should have, this is last year's slide, I should have the equation here so we can see it. Maybe I have it at the bottom. Give me a second. Yep, sure don't. So let's go back a slide real quick. So if I plug in one time constant, so basically if I make this negative RC over RC, so if I do e to the negative first power, I get 0.367. Let's call it 0.37. 1 minus 0.37 is 0.63. So this whole fraction, this percentage that I told you about, is going to be 63%. So what does that mean? It means that after one time constant, 63% of our charge has moved. And since we're charging, that means our device is 63% charged up after one time constant. I can plug in two time constants and I get 87%. I can do three time constants and I get 95%. For our purposes, we say after three time constants, we're going to consider it to be fully charged. If you do 4 and 5 and 6, you can figure out what the changes are. They become pretty small, relatively speaking. You go from like 95% to 98%, and beyond that, you can kind of do the math. So after three time constants, we consider ourselves full. We are technically at 95% capacity. It's one of those things where technically you never get a fully charged capacitor because it's always slowly increasing at this crawlingly, this real slow rate. And so we say, okay, well, yeah, technically we're never going to fully charge, but we've gotten to the point where we're getting nothing noticeable in terms of an increase. So that's what RC represents. It is called the time constant. So if I go next slide, what happens when we discharge our capacitor? We throw the switch up to S2 from S1. So we're fully charged. We throw it on there. And so what happens when we close S2? Well, at time 0, we are fully charged. Close it, you'll notice the EMF is missing because we've cut the EMF out of the picture because we've thrown it up to S2. So this is our loop rule. And so you'll notice I got two negatives. Wait a sec, two negatives, that means that I must have current going the other way. I must have a negative current so that I can actually get these things to cancel out. And we know that makes sense. Our current flowed left, up, and across to get positives on there, and now the positives are going to go back to the left, up and over. So the current through our resistor is actually going to reverse when we go through our discharging method. So that makes sense. So if we scroll down and we do the same process, so we get rid of I, we put in dq over dt, we solve for dt and dq separately, or we isolate those. I don't have to use my u substitutions already set up for me. And so we go through to a lot of the same old stuff, and this is what we get to. We get to right here. We end up with something that looks very similar. I don't have 1 minus e, I just have e. T to the 0 power gives me 1, which means at time 0, I have full charge. At time 0, I have full voltage on that capacitor. Makes sense. So looking at our time constants, what happens after one time constant? Well, after one time constant, you can punch it into your calculator. One time constant gives you 0.36787. Call it 37%. So what has happened? We have moved 63% of our charge, but it moves off of the capacitor, which means that after one time constant, we only have 0.37 left. And we have 0.14 left, and then we have 0.05 left. So you can never truly discharge your capacitor either, which doesn't make any practical sense. I agree. So again, with the time constants, it's telling us what percentage has moved. And in the first time constant, we always have 63% of our charge has moved, whether it's moved onto the plates while charging, or whether 63% has moved off of while discharging, leaving behind only 37%. So that's what those time constants mean. That's what they do for us. And so the last thing we have to look at is current. We've got our charge Q, we've got our voltage V. What about current? And so if we look through here, current is simply taking the derivative of Q related to T. And we have an equation for that now. So if I'm discharging, this is my Q equation. I take the derivative of that. I simply go to my integration tables. If I take the derivative of e to the ax power, I get the derivative of the exponent, which is a, times the same old thing. So it's actually really easy. So in going through here, I have to take the derivative of negative t over rc, and that gives me negative 1 over rc, because t is my, right here, t is my my variable. So I end up with a negative 1 over rc out front, and the rest of the equation is the same. Q divided by C, that's voltage. Voltage divided by R, that's current. So what we have here is current. So the current we have is equal to the max current times this term. Times 0 gives me a 1. So at time 0, I get maximum current. That makes sense. We saw that when we played with the capacitors the first time. Charging, the equation is a little bit more challenging, but we end up with something that is the same, because we end up with taking the derivative of a value that has t to the 0 power, so that just disappears. So basically we are doing the same thing. We have, instead of scrolling up, instead of having q times e to the negative t over rc, we end up with negative q e to the negative t over rc. So we end up with the same exact bit of math, except with a negative. So we end up with a positive solution instead. So what is this telling us? Charging and discharging have different directions of current, but the equations are the same. Think about it. At time 0, you had maximum amount of flow. When you charged it up, the bulb was brightest, and then it got dim. Discharging, the bulb was brightest, and then it got dim. All right, let's see here. So I don't have them all consolidated in one spot, charging, discharging, and the current, so you have to use those slides. So that is slide number 23. And so what I'm going to do is, if we kind of quickly go through, practice using a galvanometer, so you can do a practice question, ask as needed. So this must have been something I was doing last year, even though we did it at the very beginning this year. It must have been something I had done in the past. Again, same with this, we already did something like this, so skipping forward. Looks like this. Again, this is last year's file. Looks like we were asking some questions about voltage. The RC Circuit Lab, like I said, it produces just those wonderfully satisfying graphs, and that alone is worth doing, just because it's so nice watching those nice smooth graphs being made. But whatever. So moving forward. So here is the combination of all of our equations. Obviously the ones that are highlighted in pink there are the ones that would be on your equation sheet, and the ones kind of coming down here, you'll notice that our equations for RC circuits are not included. It's pretty common for us to leave final and max off, and we just understand what those mean. But this right here is a list of all of your equations and functions and whatnot. And then sample 1, sample 2, sample 3, sample 4, sample 5, sample 6. So a bunch of samples for you to kind of look through with some solutions. So that was slide number 16, starting with galvanometers, working our way through to the end. So that's it. This is spring break week, so I'm going to post this now, and then next week I'm not going to post anything new. I'm not going to keep on piling stuff on, besides just offering up more review UT reviews. So that is for you. That'll be posted. Today is Sunday, so this will be posted Sunday afternoon, and so you'll have it all at your hands. So this week and next week is going to be nothing. This is it. So after the first week, let's see, so if we return from spring break next week, and we have a week after that, so basically 2 weeks from today. So today is the 5th, so 2 weeks from today puts us right around the 18th or 19th of April, that weekend. I'll start looking at some magnetism stuff. But between here and now, I'm going to keep on sending out reviews and other things for you to practice as you want, as you need. So with that, it's a nice sunny day out there right now, so hopefully you're getting a chance to get outside and enjoy some nature or some sidewalks or whatever it is. But keep on working hard. Send questions as you need to, or if you send it to Remind, it pops up on my phone. I see them immediately. If you send it to Google Classroom, I'll get it eventually. If you email me, I'll get it eventually. That's not as active. So send me what you need, and good luck with everything. Enjoy your spring break. Stay healthy, stay sane, and we'll keep on doing some practice and doing some review and getting prepped up for that AP exam. I think they've kind of started sending out some more stuff, so I'll be in contact with you about what our options are there. Okay, so I wish you all, and I hope you are all healthy.